Hi, so quick question. Do you think you can tell me which one of these is frog liver tissue? Well, you probably can't because you've never seen what it looks like. You never learned what it looks like. But today, instead of teaching you how to do it, I'm going to show you how to teach your phone how to do it for you. We'll be using these algorithms called machine learning algorithms that allow your computer to learn how to recognize patterns. But don't worry, there's no coding involved, we'll just be downloading an app that does it for us. So the app I'm using is called Deep Relief by Jetpac, and what I've already done ahead of time is separate the slides I'll be using into a training set and a testing set. And the reason why I do this is because if we want to check whether or not this algorithm can actually tell the difference between different types of tissue, we want to test it on something it's never seen before. Because otherwise it'd just be able to match it up. And it'd be kind of like providing a practice question with the answer and then putting the exact same question on the exam. It's not a really good test. And so what I'm doing here at the beginning is I'm teaching it how to recognize frog liver tissue by showing the algorithm the training half of the frog liver section. Then after it's done with that, we need to show it examples of things that aren't frog liver so that it can compare between the two and identify the key characteristics or patterns that are unique to frog liver. And to further explain what this algorithm is doing, let's give an example using a stop sign. Assuming we taught this algorithm, called a deep convolution neural network, how to recognize a stop sign. This is a simplification, but basically what happens here is that there will be a neuron that combines all the signals from a bunch of individual pixels and recognizes the relationship between these pixels as the letter S. Then there's another neuron that recognizes a T, another one for the O, another one for the P, another one for the overall octagonal shape, and another one for the overall red color. Then there's another neuron a layer above that combines the signals from the neurons that are saying STOP, octagon, and red color, and recognizes the relationship between these characteristics as a stop sign. So basically, the general idea is that it groups together smaller parts of the image based on their relationships, then takes those groups and their relationships to form new, larger conceptual groups. And in our case with these tissue sections, it might be looking at the small purple spheres, striations, shapes, colors, density of things, and etc. Which brings up another interesting point that's really nice about neural network algorithms, is that it's a general purpose algorithm. Because of the way it recognizes these relationships, it's very flexible in what it can learn, which makes sense because it's based on how our brains learn. But this algorithm also has certain limitations that you can see in this app, mainly that it's generally computationally expensive. It takes a lot of calculations for it to learn something, because it doesn't scale well the more stuff you show it. For instance, if the training set was 10 times bigger, the number of calculations wouldn't just be 10 times more, it would be more like 30 or 50 times more. Basically, it's not a linear relationship, it's more exponential, which is why this app automatically drops the camera resolution substantially, and also limits the amount of time you can spend showing it what you want to learn and the counterexamples. Now that the training is done, let's see how well the algorithm does on the testing set, which is the bottom half of each section. And how confident the algorithm is that it's looking at the frog that we showed it before is represented by the blue bar on the top left of the screen. And as you can see, it does a really good job. It's very confident that it's looking at the frog liver, even though the algorithm has never seen it before and can't do a one-to-one match. And you can tell it's only when I'm looking at the frog liver and pretty much any part of it. Now we're going to try showing it the testing set of the sections that we taught the algorithm isn't frog liver. This is just as important, but luckily it's very confident when it isn't looking at the frog liver we showed it before by showing roughly 0% confidence. And now we're going to start doing something really interesting. We're going to start showing it new types of tissues that weren't in the training set that it's never seen before. And what we're wondering is if it faces any kind of issues with false positives. So we're trying a bunch of different tissues that look similar, and we're going to try to see if we can trick it into recognizing this as what we showed it before, which was liver tissue. As you can see, it's doing pretty well. And even though frog liver was kind of an easy example relative to the other slides, and we haven't really tested it very extensively, really this is pretty amazing for something that you can do on your phone. Not too many years ago, we were struggling to get clusters of computers to recognize the difference between the written number 1 and 2, and now we can recognize the difference between microscopic tissue images on a phone. Now here's an example that I showed because I knew if I showed it that frog liver and those counterexamples, it would have trouble with this slide, which is a dog cardiac muscle. And maybe this is because the finer details are somewhat lost from the resolution drop, and the slide looks kind of similar with the density of those dark purple dots on the lighter background, but either way this slide trips it up. It seems about somewhat confident that this is the frog liver that we showed it earlier. However, when I include the cardiac muscle in the training set as part of the counterexamples, it does a fine job at recognizing when it is frog liver and when it isn't. And I want to show you this as a disclaimer that this isn't perfect yet. It won't replace your histologist. Right now with this limited app, it's more to show you something cool and how we're getting very close. But of course that doesn't mean we'll never get there. Computer scientists, engineers, and programmers are constantly making these algorithms more accurate, efficient, and accessible every day. In fact, the SDK for this algorithm is available from the Jetpac company on an open BSD license. Although they do make it clear that it wasn't particularly designed around identifying liver tissue. Maybe you'll be the one who'll improve on this software and technology. Eventually, there will be the software that combines a digital microscope with an internet-connected computer to really become the world's first smart microscope, or as some may call it, the Tricorder. And this is one of the first baby steps in that direction. Now, if you want to do this at home, you can kind of fake it by downloading the app and showing it pictures of slides on your computer screen, or maybe print them out on paper. But it isn't quite as fun as doing it for real. And so if you're wondering about the microscope I'm using here, it's actually a microscope I designed myself. And I like it a lot because it's powerful, it can produce over 1,000 magnification, and it's really versatile. A 10-year-old might use it to satisfy their curiosity, but a PhD or other professionals can use this to satisfy their needs. And another nice thing about this microscope is that in the next iteration I may include fluorescent microscopy, which is when you use glowing antibodies that attach to specific biological markers. Now imagine overlaying that information on top of the light microscope image and then feeding that into a machine learning algorithm. It makes it possible to get a very accurate identification. This is truly a next generation microscope, and if you want to find out more, feel free to click on the link. But otherwise, thank you for listening, and I hope I showed you a really cool trick today.